Quantum theory, quantum physics, a term that even in the modern day is wrapped in mystery. But where does it all start? How are we to go about interpreting it? What does it mean for all of us in the real world? These are some of the questions that we'll journey into and hopefully find some sort of explanation. A good place to start is the nature of light. For the past few centuries, the nature of light has been debated. Isaac Newton believed that light itself was made up of tiny particles or corpuscles. This theory prevailed for some time until light was finally championed as a wave. Young's famous double-slit experiment is an important investigation in the history of the nature of light, and its basic concept is important for quantum mechanics. Direct evidence for the wave nature of light is uncovered through an effect called interference, a key concept in both classical and quantum physics. It can be thought of simply as the combination of two waves. This is an example of constructive interference. The final wave is the result of the principle of superposition. This principle states that when two waves combine, the resultant amplitude is calculated as the sum of the two amplitudes. Constructive interference occurs when the waves are in phase, and thus add together to give a wave of greater amplitude. Had the waves been out of phase by a multiple of pi, however, the resultant amplitude would have been zero. This is an example of destructive interference. Why is this all important? Well, it turns out that Young's experiment shows that light itself interferes and therefore must be a wave. In his experiment, Young fired monochromatic light, which is light of single wavelength, towards a screen with two slits. The light passed through and was received by a second screen. On this receiver screen, a pattern of alternating bright and dark fringes can be seen. The bright fringes correspond to points where the light is interfered constructively, and the dark fringes correspond to points where the light is interfered destructively. By showing that light passes through and shows interference, Young had essentially shown that light was a wave. So this is great. Light's a wave, or so we thought. This is where we come to Einstein. The photoelectric effect had been known for some time before Einstein, and a detailed explanation had been provided of it. The effect itself is a phenomenon whereby electrons are emitted from the surface of certain metals when light above a certain frequency is incident. Einstein saw a problem in the wave model of light. It was known that atoms could absorb and emit light. How could it be possible that something that's spread out as a wave could be absorbed by something so localized as an atom? The photoelectric effect only provided more issues for the wave model of light. The intensity of light and its amplitude are related by the relation I is equal to Ka squared. This essentially means that the intensity is proportional to the amplitude squared. However, in the photoelectric effect, it's noted that a higher frequency does not increase the energy of the electrons emitted. What was more disturbing was the fact that the frequency of light, as it was increased, resulted in the electrons having a greater energy when emitted. Einstein solved this problem by deciding that in the photoelectric effect, the incident light behaves as a particle. These particles are known as photons, where a single photon is a quanta of electromagnetic radiation. This is essentially the basis and the start of quantum theory. So, we have now experiments that contradict each other. On the one hand, we have examples of light behaving as a wave. On the other, we have examples of light behaving as a particle. But which model is correct? The situation becomes even more distorted when we perform a modern-day equivalent experiment of Young's double slit. It's possible to recreate this experiment, but instead of passing a beam of light through, we can pass a single photon at a time, or even an electron. What do we expect will happen? Well, when you pass a single photon through, of course, you expect it to hit the screen, and it'll be detected. In this example, let's say that when the photon hits the detector screen, it causes a little dot to appear. That's fine. What happens if we pass another photon through in exactly the same way? We can repeat this step many times, firing photons individually, and looking at the result on the detector screen. What do we see? It turns out that we actually get an interference pattern. But how has this happened? We pass the photons through one at a time in exactly the same fashion. Photons are particles, yet somehow they've managed to display some sort of interference, something that only waves are expected to do. Is it possible that the photons are behaving both as particles and waves then? Moreover, we pass the photons through by themselves. How have they managed to interfere? Does a single photon interfere with itself? Does this mean that the photon is somehow in two places at once? The answer to this problem comes back to the principle of superposition, and this is where quantum mechanics kicks in. We say that the photon has an associated wave function. The wave function consists of a superposition of states. In this example, you could think of one state corresponding to going through one slit and the other corresponding to going through the other slit. The photon exists in a weird superposition, going through each slit. When we finally make a measurement, the wave function is said to collapse into one of the states, and this corresponds to the measurement on the detector screen itself. This leaves us in a pretty good position to start looking at the famous Copenhagen interpretation of quantum mechanics.